Hello, students. This is a little another mini lecture, maybe medium-sized lecture. It will be on the last two sections of chapter 9, encryption, with a particular example of RSA. So I want to go over this just to illustrate some points about it. You can read it in the book, of course, but also it like really nicely captures several things that we were talking about in this segment. So maybe you will find this helpful. Okay, so the general setting of an encryption is that you have two algorithms, an encryption algorithm that in general, these are randomized algorithms, but just think of them as functions. It's a function that takes two arguments, a key and a message, and maps a key and a message into a cipher. And it comes with an inverse function called decryption, which takes a key and an element of the ciphertext and outputs an element of the plaintext space. So M is called plaintext space or message space. K is called key space. So that's the set of where the keys are going to be chosen. So choose key K at random in the space, in space K. That's the meaning of the key space. And C is the ciphertext space. And I say space, I mean sets. Right, so this is the set of all the plaintext, this is the set of all the keys, this is the set of all the ciphertext. But these are large sets, so customary terminology is to call them spaces. We have two types of encryption schemes, broadly speaking. One is called symmetric encryption, the symmetric encryption has the property that an encryption key, the key you used to encrypt, is the same as the key that you use to decrypt. So there's a single key, and it's given to both the party who encrypts and the party who decrypts. But there is a different way to do it. It's called public key encryption. For a long time, it was not known how to. There were no examples of such a thing until the mid-70s, and where Rsa, Veneer, and Adelman gave the first such example of what became known after their last names as RSA, public key cryptosystems, where the encryption key and decryption key are actually two different strings. And not only they're syntactically two different strings, no, moreover, even if encryption key is public, so you broadcast this public key widely all over the world, encryption, decryption is still secure. And can only be done with the decryption key. Okay, so I'm going to create two keys: the decryption, which I will keep privately, and the encryption, which I will broadcast all around. And the guarantee of the crypto system is that even though this encryption key is broadcast all around the world, as long as I keep this decryption key private, nobody can decrypt but me. Okay, so the encryption schemes have to satisfy the following, what I'm going to call it, correctness requirement. And it's a requirement that no matter what key is chosen, and let's take symmetric encryption for the time being, that I choose some key in the key space, and I choose any message in the message space, and if the ciphertext is computed as running the encryption function on the key and the message, then if I run the decryption function on the same key and the resulting ciphertext, it will output the original plaintext, right? So if encryption used some key to map a message into a ciphertext, and then the same ciphertext was run through the decryption function using the same key, then the guarantee is that the original plaintext will be spit out, right? So the application of this is that there is some Alice who has a key K. She gets some message that she wants to send to Bob, and Bob has the same key K. These are the inputs of these two players. She will run the encryption function on her key and this message. This will give her a ciphertext. She will send the ciphertext over to Bob. The Bob will locally take this, apply the decryption function, and output M. And the correctness requirement basically means that this thing output here is the same as what Alice wanted to send, right? So if nobody interferes with this, first of all, if these two guys really have the same key, and nobody messes with the ciphertext on the way between Alice and Bob, then it will be dandy, right? And now what about security? So correctness, so far so good. What about security? Well, the idea is that adversary hears ciphertext C, because if there was no people in between Alice and Bob, if this was some sort of safe channel, then there would be no reason to encrypt. But you encrypt because you believe that, you don't feel confident just sending a plain text over. What if somewhere in the long path of the internet is somebody spies on you, right? So you encrypt. Well, for the same person who is sitting somewhere there, what do they get? They get this ciphertext, right? So that's what's traveling between one internet node and another internet node, or whatever it is, wireless node, right? Wherever this encryption is implemented, whatever the communication medium here. So adversary hears the ciphertext, but if key K, which Alice and Bob use, is random in key space K, right? So that's how little key is chosen. At the beginning, they chose it at random in key space, and somehow magically, and this is actually a problem in crypto systems, like who picks this key, and how come it ends up on the two sides, the sender and the receiver? Okay, but if this was done, then under the assumption that this was correctly picked, adversary learns no or little information on message M. So he gets the ciphertext, but his real question is, what is the plaintext? That's what he wants to learn. And what the crypto system will give you is that as long as this key is random and adversary doesn't learn anything about it, then the message should be somehow scrambled by the ciphertext C. Okay, that's the encryption goal. Okay, so let's see one example of it, a very, very simple example. It's an encryption scheme we call it, number 1. Okay, and it's, excuse me, it's covered in section 9.8. It's like a preliminary to, setting the terms for crypto systems. And actually, there is a name of this crypto system. It's called a shift cipher. Okay. How does it work? The message space is Zn, which is all the integers from 0 to n-1, for some integer n. Okay. The key space is also Zn. Okay. And we assume that the key is chosen at random from this key space. Okay. Now, encryption, the shift cipher encryption, using such a key and such a message. So both key and message are elements in this space. Some integers between 0, some residues mod n. And what you do with them is that you simply add them mod n. So note, first of all, that what is the space of ciphertext that you get? Well, it's also Zn, right? Because what is output by a procedure that takes 2 elements mod n and adds them mod n? Well, it's another residue mod n, right? So this will always output some number in mod n. Okay, and how do you decrypt? You take a ciphertext and a key, and you subtract the key. Okay, well, correctness, you can all see it, is that if ciphertext is computed as n plus k mod n, then if I use the same key and decrypt that ciphertext, what do I get? Well, I get if C is n plus k, so therefore I can do this, and I subtract k mod n. But modular reductions done in between steps don't matter. So I can just rewrite it as this, right? So it's like whether I perform this modular reduction here or I just postpone it, it doesn't make a difference. And so here you can see these cases cancel out. So this is just m. And well, literally it's m mod n, but it is really m because m was assumed to be smaller than n, right? Because m was in here, right? So modular reduction on m does nothing. Okay. So simply you added a key when you encrypt, and you subtracted the key when you decrypted, and obviously that cancels. Okay. So, well, all right. So in the book you have examples of that, and so you have some on the homework. So let me tag these things. So remember when I post them to put them in correct order. Well, you can generalize this, and one way to do so is that it's actually called Veneer Cipher, where the only change that we do is that this is now a sequence of T elements in this space. So this is the message in this matrix space is a sequence of T elements such that for all I, mi is some residue mod n. Okay, so think. So where can you use it? So okay, so think n is 128. What's the n? That's ASCII. Right, it's from 0 to 127. So M is T long ASCII string. Okay, but you know, take N is 2 to 16. Okay, so then the N is I believe this is called int in C. Okay, or long, or okay, I actually, sorry, I forget. Right, so 16-bit has an, you know, it's a standard size of registers, right? So you can take 32 or 64, right? So these are the standard parameters. And this, by the way, is 2 to the 7, right? Okay, and what does Veneer Cipher do? So here is its let me write it on a new page. So message is a T character long sequence for all I. Mi is an element in the CN space. Key is also going to be like this. Okay, so the key is K1, K2, KT. Okay, and again, for all I, Ki is in Zn. And how do I encrypt? Okay, encryption is as I just do pairwise shift cipher, but at every index. So in other words, ciphertext is a string also in ZMT. So it's also, you know, if these things were ASCII, then this is an ASCII string, right? I don't change alphabet, so to speak, from the plain text to the ciphertext. And the encryption works like this: for every I, 1 to T, Ci is Mi plus Ki mod n. So the shift cipher just didn't have these indexes. So a single value was a message, and a single value was the key, and a single value was the ciphertext computed. That's the sum of the message and the key. Here, I have a string of values, my message, string of values with my key, and I compute ciphertext by just applying the shift cipher index by index wise, right? So the second ciphertext character is a sum mod n of the corresponding message and key characters. The third, M3 plus K3, would be C3, and so forth. And how do I decrypt? Well, of course, I apply the shift cipher back character-wise, right? So for all I 1 to T, Mi is computed as Ci minus the correct index of the key, so correct character of the key, right? And correctness follows from shift cipher. Sort of, these are basically independent shift ciphers at every index. Okay. So look at another example. Take another example. Do the same. So what I call here Veneer, although Veneer, when you actually, that term is more appropriately used, key ends at some point, and messages don't. And the same cycle of keys is then reused again and again for every block. So it's like, say I had 6 keys here, I would take 6 characters, do this, but then for the 7 characters, I'm going to reuse these key characters later on. Okay. Well, that's an important detail because that's really not a secure thing to do, actually, but let's keep that. And just think of the cipher this way. But take the modulus, a very simple modulus, 2. In other words, what is Z2? Z2 is just bits. So now my characters here are just bits. Okay, so the message M1 to MT is a bit string of length T. And the key is also a bit string of the same length. And encryption of key and message, well, I use this encryption, which means that this is a bit string such that at every index, CI is MI plus KI mod 2. But this function has its known mod 2. You know it by a different name. It's an XOR between the bit of M, these two bits. Adding mod 2 is the same as taking an XOR. So you can check that, take M and K, and let's look at the XOR table. So what are the possibilities? Just these four. And what's the XOR table function? At 0, 0, XOR is 0. It is exclusive OR, right? So it's true whenever OR is true, except when both M and K are true. So it's 1, 1, 0. That's the truth table of an XOR. And compare it to M plus K mod 2. So now let's treat these not as bits, but as integers and perform addition mod 2. Well, 0 plus 0 is, of course, 0. 0, 1, 0 plus 1 or 1 plus 0 are 1. And 1 plus 1 is 2. Mod 2 is a 0. And, well, obvious conclusion is that these two are equal, right? So it is the same function. Okay. So in other words, this encryption, yeah, I can write it in this way. It just takes an XOR of these two strings. So what this designates is a bitwise XOR between strings M and K. And the decryption inverses that by XORing this key again, right? And really correctness follows from the same equations, right? Like with just N2. But let's look at this with a fresh eye. Why is this? Why is this correct? Okay. Well, let's look. C XOR K. C is M XOR K. It's M XOR K XOR K. But that's the same as M XOR K XOR K because XOR is commutative, right? So I can. It doesn't matter what order I'm XORing. Just like and OR, XOR, you can check, it's also commutative. So that means this guy cancels and this is M, and that's the correctness, right? And you can check, take some small example, message, let's say 01101, key 10111. Okay, so what's the ciphertext? It's an XOR of these two. So a bitwise XOR, 01 XOR 1, 10 XOR 1, 11 XOR 0, 10 XOR 1, 11 XOR 0. Okay, so let's decrypt. I use the same key, 10111, and I XOR to decrypt. And what do I get? 1, 1 XOR is 0. This is 1, 1 0 is 1, 1 1 is 0. And beautiful, I have the same string, right? Okay. Now, just one more word on this before we move to RSA, which is, why is this called one-time pad? Okay. So why do we call this one-time pad? Because actually spies exactly use this algorithm, right? So again, this is T characters, all of them in some space. So in binary, these are bits, but you can use other alphabet, right? Like you can use English letters. So this could be one of, n is 27, and this is a number between 0 and 26, each of these encoding a particular English letter. A key is also a string of the same alphabet. So binary on the slide before, and English alphabet characters, in the 19th century spy novel. And basically a cipher is well, this M plus K mod n, but character-wise, right? So at every index, we apply the addition. Okay. So take binary. Okay, like on the previous case, previous slide. Then I can write this encryption as XOR between. So it's a bitwise XOR. What happens if, so what the spies needed to do is that when they had some, let's say this was one, I don't know, 200 characters. So they wrote on a piece of paper 200 characters, and they should use them only to encrypt a string that has only 200 characters. They should only use the key one time. In other words, if they have already enciphered by this character-wise addition, position-wise, maybe I should call it better. Okay. Then they should strike out these key characters, in fact, burn them or something, right? Because whoever gets a hold of these can now decrypt. The security of this works if these characters are random, then this addition permutes mod n. And if you don't know what the shift is, and the shift is chosen at random, then mod n, you just mapped any character to a random character. So that's where the security of a one-time pad comes from. But what happens if you did reuse the key, like I said, Veneer Cipher would? Okay, so let's see that. What if you use same T-bit PK to encrypt two messages? MA and MB. And both of them are in the proper space, so they're both T-bit messages. So what happens then? Okay, that it's simple to see. So look, if I use this key to encrypt MA, I got some ciphertext CA. It's an, again, T-bit long string. So far, so good. But if I reuse this key, then I encipher message MB, like so. And now note that all the adversary needs to do is to take these two ciphers and XOR them. Because then this is MA XOR K, XORed, and B XOR K. But by commutativity of XOR, this is the same as MA XOR MB, XOR K, and XOR K again. But this cancels, so this is MA XOR MB. Now, you can say, well, so who cares if an XOR of two messages leaks? Well, unfortunately, that's a lot of information. So here, think of the simple case. Adversary knows immediately that you have re-encrypted the same thing. that there was some place in the message, on the first message, let's say from 2nd to 10th character, that was the same as in the other message, because the XOR of the two would be all zeros. And that's if the XOR between these is all zeros for some fragment, then it means that on that fragment, MA and MB were the same messages. And that's already a lot of information, you know. For example, let's say this is military stuff, and you're like saying, you know, where we are at some point in the message. So now the adversary knows that you're in the same place, right? Or whether there was a date, so now he knows that it's the same date, and on and on and on. But it's actually worse than that. If, you know, if MA and MB are ASCII, okay, so you know, basically N is 200 is 128, right? And then MA and MB are English sentences. Well, they think of lower capital letters, right? The capital letters are lowercase letters, so right are infrequent. So there is only 27 characters out of 128 that MA and MB are effectively made of, right? So once in a while there's some other character, but most of them is one of the 27. So this is a tiny subspace. So this is all 128, and this is the 27 English letters. So if I take a sentence made of this small subspace and code them in ASCII, and then I take another one made of these, and I give you the XOR between these two bit strings, you can basically search over these, all the possibilities of 27 possibilities for each of these, and 27, which will give you the XOR that you observe on that position. And even if there is some choices still remaining, you basically do a dictionary search for close match with actual English words, and you eliminate all the possibilities that were nonsensical. So this basically means that you can, you know, can recover both MA and MB. Okay, if they're long enough. I mean, if they're like a single letter, then perhaps not. Okay. So, all right, let's move to RSA. RSA, it's the section 9.9. Okay, so RSA is an example of a public key crypto system, and a public key crypto system is has one more complication, or two. It's a triple of algorithms: key generate, encrypt, decrypt. Encryption and decryption basically work as before, but key generation is different. And namely, when you run a key generation, it generates at random, not a single key, but a pair, public key and a secret key. And when you run encryption, you run it on a public key. So the public key is used to encrypt, and the secret key is used to decrypt. And when you run encryption on the public key, it gives you some ciphertext. And when you run decryption on the secret key and that ciphertext, it gives you the message back. And usually public key defines message space. Okay, so without loss of generality, public key defines a message space. Okay. Now let's look at the RSA example. Before that, let's just maybe explain the motive. How will this be used? Okay, so it's application is as follows. Everyone on the network, okay, so let's say every UCI student or every internet server, everyone on the network runs key generation to create their own random public key secret key pair. Everyone keeps their private key SK securely. If this thing leaks, then my security is broken, because everybody can run the decryption algorithm now on the ciphertexts that were created for me. But everyone broadcasts their public keys. And if you just look at an Alice and Bob, okay, so here is Alice and here is Bob, and I'm going to have Bob generate his private key pair, and he will broadcast. So in particular, he will tell Alice what his key is. And now when Alice has some message, she will use an encryption algorithm that runs on the public key that she received from Bob to create a ciphertext. She will send the ciphertext over, and Bob, who keeps the secret key, is going to use it to run the decryption, which outputs the message, right? And of course, correctness now, yes, is that for every generated secret key public key pair, for every message in the message space, if C is an output of this procedural function, then the original message will be output by the decryption on this ciphertext, right? So this relation, this implication will hold, right? If you run encryption on the PK and decryption on SK, I see this is got out of, hold on, let's refocus. Okay, where they were generated together, okay, by this key generation algorithm. Now, what about security? Well, that's a little more complex, right? But intuitively, what's the difference? The difference is that in the symmetric key example, right, we said adversary just had no information about this key. It just was distributed between Alice and Bob behind the, behind the curtain, and the only thing he sees is ciphertext. Here, in addition to ciphertext, he sees the public key, right? So intuitively, given the public key and ciphertext, is still hard to create a message M without the secret key, right? So that's the kind of guarantee that I mean, that's what encryption, public key encryption needs to do. Okay, so in this class, we will not talk about what's the basis of security for RSA. I very much invite you, later on maybe to take a crypto class to learn that kind of stuff. But we'll just show what it is and like why it's correct at least, right? So let's move to this specific RSA example. And so RSA crypto system looks like this. Key generation works like this. It has several steps. First, it pick two large random primes, P and Q. And how long? Well, in practice, let's say 100 bits, 1,000 bits, 2000 bits. Okay, something on that order. Of course, in our case, it's gonna be small numbers, right? We'll only show examples for small numbers, but this is why we need to know how to choose primes of this size relatively fast, and how we need to assure that these are primes. Okay, I mean this algorithm and others like it. RSA is not the only case. So you pick these two large primes. Now you compute what's going to be a modulus n as a product of these two primes. But you also compute a secret number that I'm going to designate phi of n, and you compute it p minus 1 times q minus 1. And the note book calls this simply phi. It doesn't say phi of n, but phi of n is a more general notation, okay? Because it's a function of the modulus. All right. The third, you pick a small integer e such that it is coprime, so the GCD between e and this phi of n number is 1. Okay, so e is coprime with this, not with the public modulus. Okay, well, you'll see in a second what's private, what's public. And now compute a multiplicative inverse of e mod phi of n. And if you remember Euclidean algorithm stuff, that because if e and phi of n are coprime, then this exists, right? So I was kind of drumming on this point with a few examples of modular arithmetics that you were going over. And here is an application of it. Okay, and you're basically done. Now you just output the private and public key. The public key is modulus n and exponent e, and a secret key is also modulus n, but this exponent is d, the multiplicative inverse of e modulo phi of n. Now, message space is m is z and star, and that's a set that we defined at some point, but I will define it once more. It's all the moduli, all the residues mod n, such that these these residues are coprime with the modulus. Okay, and if so, this is the message space, and this phi of n function is actually defined as the size of this space. Okay, it just happens to be that if n is product of two primes. Two facts about phi of n. So first of all, if n is prime, then phi of n is simply n minus 1. Okay, and that's kind of obvious because if n is prime, then z and star is all elements. And if you count them, that's n minus 1. So z and star is indeed n minus 1. Has so many elements in it, right? And here is an but in the case of RSA, we are concerned with the modulus, which is a product of two primes for p and q prime. And in that case, phi of n is computed in this way. And you can check, not hard to see, that z and star must be of this size. So it contains all, it's n minus the number of p multiples minus the number of q multiples, because how can I not have a GCD with n1, right? I have to be a multiple of p or a multiple of q. These are the only factors of n, and they're prime. So it's impossible to be not coprime with n unless you're a multiple of p or a multiple of q. But you are overcounting if you do this. And how many multiples of p there are between 1 and qp, q of them? And how many multiples of q there are between 0 and qp, it's q of them. But you're overcounting. There is one common, it's a 0. It's yeah, it's counted twice in here. Okay, and so that's why this is n minus p minus q plus 1, and since n is p times q, it's p times q minus p minus q plus 1, and you can see that this is the same as that. Just cross multiply it and you will get p times q minus q minus p plus 1. Okay, so that is an elementary argument that this is a correct expression for the number of residues which are coprime with n if n is a product of two primes. Okay, so let's move to encryption and decryption, of course. All right, so I will just tell you the basic, or copy the basics of the key generation, so you can see key generation was n is p times q, phi of n is p minus 1, q minus 1, pq are prime. Then E was such that it was coprime with phi of n, and D was a multiplicative inverse of E mod phi of n. Okay, and the public key is defined as NE. The secret key is defined as ND, and the message space is a ZN star, which is all the messages which are modulars of U mod n, such that they are coprime with the modulus. Okay, that's key generation. Now, how does encryption work? Okay, it's actually simpler than this. It's short, faster to write. Encryption that uses the public key and the message, assuming public key is n and E, outputs m to the E mod n. So this is the ciphertext. It's computed this way. When you decrypt the ciphertext, and here you assume that the secret key is a modulus n and exponent d, what you output is that you take the ciphertext and you exponentiate it to d, and you also do it modular exponentiation. So that's the plain text decrypted. Okay, so well, you've seen why we needed primality testing to choose these random and long, right? To choose these primes. You see why we needed all this inverse stuff to be able to compute this. And here you need fast exponentiation, right? E is going to be, E actually will be a small integer. So E is small. So perhaps here you don't need fast exponentiation, but D, the multiplicative inverse, is going to be some number mod phi of n. Now, if P and Q are large primes, let's say this is 2000 bits. So phi of n is also of the similar size. Yes. So you take a modular reduction. This has 2,000 bits. So you need fast exponentiation to do this, right? Okay. Now, this is the algorithm itself, right? So this is RSA algorithm. RSA correctness follows from a general theorem that is called Euler's theorem. And the theorem is this, that for any integer and for any residue that is coprime with this modulus n, if I take this residue to the power phi of n, okay, where phi of n is the size of this group. I mean this, yeah, okay, this set. And I compute this exponentiation mod n, I get a unity. Okay. And you can go back to your multiplication tables, mod 5 or 6 or 7 or 8 that we have done in the textbook, in the discussions, in the homework. And you will see that this relation always holds. So like the n was either prime, in which case phi of n is n minus 1. So you see that if you do exponentiation mod 7, once you multiply anything 6 times, you get a 1. Okay, so that would be true in mod 7. If you had mod 8, well, phi of n actually for mod 8 is very small. So 8 is not even a product of 2 primes. It's just 2 times 2 times 2. So phi of n, okay, I forget what it is. I think it's only 2, really. So multiplication, exponentiation mod 8 is sort of very uninteresting. Very quickly, you get anything exponentiated to, I think, 2 already is the 1. Okay. But if this is prime, then you need to exponentiate this prime minus 1, and only then you hit a 1. Okay, it's not true. It's only then for some m faster. But the point is, for all m, once you get there, you always get a 1. Okay. Now, a consequence of this this is, for our case, look, if D is a multiplicative inverse of E mod phi of n, then by definition, if I multiply these two, I get a 1 mod phi of n. And therefore, if D times E is 1 mod phi of n, what does this mean? If I move 1 on this side, so if I look at DE minus, well, okay, all I need is this. DE is 1 plus some multiple of phi of n, right? For some integer k. Yes, for some integer k. Well, that's what it means, right? That DE is 1 modulo phi of n. So some number of phi of n's plus 1 gives me DE. Okay, so this is actually not a consequence of this. It's just note. We'll use it to show RSA correctness using Euler's theorem. Okay, so now this consequence is RSA correctness. Why? So if C is m to the E, like it should be, right, when you encrypt, then let's look what's M prime that is created by decryption. If I stick M to the E mod n for the ciphertext, I can rewrite this as follows. This is my C, and now I take it to the D mod n. Now you know that this is a bunch of multiplications and modular reduction. So it's a multiplication with mod n, and then result exponentiated mod n. I don't need to do this reduction. I can postpone it. For efficiency, it would make no sense, but it's still true. So this is the same as that mod n. Now this is the same as M to the E times D, right? But M to the E times D is the same as M to 1 plus K phi of n, right? Because I set my E times D precisely to satisfy this, right? I set this right here. This key equation maps to this relation. And now, okay, let's rewrite it. This is M to the 1 times M to the phi of n to the K, right? Because that's how arithmetics work. Like M A plus BC is the same as M to the A times M to the B to the C, yeah? So that's all I did. And now we're basically home, because this is the same as M to the 1 times 1 to the K. Because by Euler's theorem, and all of these operations are mod n. I'm going to have, like, whatever I do here, at the end, I'm going to have mod n, which means that all these operations are mod n. So in particular, what happens inside here is also what I care is mod n. And by Euler's theorem, M to the phi of n mod n is just a 1. So this simplifies like so, and of course, 1 to whatever power is just 1. And this is number 1, right? Which I just carried for no reason, because this is, of course, just M. M to the exponentiated to 1 is just M. And all of this mod n. And so now I have that the decrypted M prime is the same as the encrypted M. Okay, so this shows correctness of the of RSA. Well, if you want to bear with me for a little longer, then I will just go over an example of this for some particular parameters. Just so, right? There are examples in the textbook, and there will be examples in the discussion, and the homework asks you to go over this for some particular numerical examples. Okay, so let's do one of these quote unquote together, right? It's just me and a camera. Okay. So let's do this. Let's take an example for P3 and Q5. Okay, so the RSA, here is the general algorithm. Okay, so example P3, Q is 5, they're both prime. Okay, so N is P times Q, so that's 3 times 5, 15. Phi of N is P minus 1, Q minus 1, so 2 times 4, 8. Okay, what's the message space? All right, so the message space is Zn star, which is Z15 star. Okay, so who's in it? Let's say these are residues, mod n, which is 15. So basically from 0 to 14, right? but residues which are coprime with the modulus, which is 15. Okay, so 0 is not coprime with anything. 1 is coprime with everything. 2 is coprime with 15, right? So 15 has only 2 factors, 3 and 5. But 3 is not coprime, so it's out. 4 is okay. 5 is not coprime with 15. 6 is divisible by 3. 7 is fine. 8 is fine. 9 I cannot because it's a multiple of 3. 10 I cannot, it's a multiple of 5. 11 fine. 12 out, multiple of 3. 13, 14, and that's it. And you can see that indeed the size of this group is 8, which is phi of n. Okay, so so far so good. So let's take a small integer, like let's say 3 will be your exponentiation exponent. And what's d? Well, d is e minus 1 mod phi of n. But for our numbers, this is inverse of 3 mod 8, because that's what phi of n is. So what is such a thing that if you multiply 3 by it, you get 1 mod 8? Well, I can tell you it's 3, right? Because d times e is 3 times 3, which is 9, which is 1 mod 8. So it's a simple guess. So the public key NE is modulus 15 exponent 3. And oddly, the private key is the same. This is coincidence. You know, you have small numbers here. There's not many choices. But also, this mod 8 stuff is such that arithmetic mod 8 is very primitive, as you might have observed, like doing this previous homework. So actually, no matter what I take, the inverse of it is the same thing. So 5 times 5 is 25. That's also 1 mod 8. You know, and what about 7? Well, 7 times 7 is 49. That's also 1 mod 8. So it's like whatever I took, the inverse of it is the same thing. Mod 8. Okay, no matter. Let's now. So what's the encryption and decryption, right? Encryption of any m. So for any m in this space of Z15 in this space, encryption of m under this public key will be just m to the 3rd power mod 15. And the decryption of using the secret key of any ciphertext, right, is ciphertext to the 3rd power s of mod 15, right? Because e is 3, right? So e is 3, and here I use the decryption d3 as well, right? So that's why I have 3rd powers in both cases. So perhaps look at let's make a table of possible messages and the corresponding ciphertext, right? Which is m to the 3 mod 15. So what are the messages? 1 in the ciphertext, in this message space. 1, 2, 4, 7, 8, 11, 13, 14. Okay. Well, 1 to the 3rd is very simple one. It's just 1. 2 to the 3rd is 8. 4 to the 3rd is like 16 times 4. 16 is 1 mod 15, right? So it's 1 times 4, so it's just 4. So this is mod 15 operations, right? 7 to the 3rd is 7 times 7, so 49 times 7. 49 is, what's mod 15? What 45 is the multiple. So this is 4 mod 15. So this is 28. And mod 15 is 15 plus 13. Yeah, so this is 13 mod 15. Everything here is mod 15, what I'm doing. Okay, so 8 to the third is 64 times 8. 64 mod 15 is 60 is the nearest multiple. It's 4 times 8. And this is 48. What? No, 16 times 2, 32. Okay. And mod 15, that's a 2, right? Because 30 is 0. 11 to the third is 121 times 11. 121 is just 1. 120 is a multiple of 15, right? Because it's a multiple of 30. So this is 11. 13 to the third is 169 times 13. So 150 is a multiple, obviously, and 165 is. So this is 4 times 13. And so 4 times 13 is 52. So 52 is a 7, right? 45 is the multiple. And 14 to the third, you know what? I'm going to use a trick. 14 is a -1 mod 15. So this is going to be much faster, obviously, to compute, right? Because this is just -1. And so this is 14. Okay. I could have used -2 for 13, and it will give me a correct answer. What is -2 cube? Well, it's -8. 7 is -8 mod 15, right? So you might notice that these two sum to 0. These two are, this is -8. 11 is -4. 2 is -13, right? It's not coincidence because this guy is a minus this one is a minus this one. So if you cube them, the same correspondence will hold. Okay. So what did we get? M and C was M cube. The table was 1, 2, 4, 7, 8, 11, 13, 14. These cubes are 1, 8, 4, 13, 2, 11, 7, 14. So what do you think this now decryption? So M prime is C cube. Okay. Okay, this might look like, okay, well, I will just call it C cube. How's that? Okay. Well, it's the same function. Cubing, when you decrypt, you cube in this particular case, right? Where both encryption and decryption exponents were 3. So it's really, you apply the same function to decrypt. So to decrypt 8, you just need to know what's a cube of 8. It's a 2. And ta-da, the cube of 8 is the same as this. So what has happened here? How much what power did you take? C3 is M3 to the third, and that's M9, and that's M mod 15, because M to the 8 is 1 mod 15. Oh, sorry, mod 15 for every M by Euler, by Euler's theorem. Right? So you always, taking stuff to the 9th power always will come back to the original input, because taking to the 8th power is an identity. Okay? So you will always get basically M back, right? But you can check, well, 1, of course, cubed is 1. 4, well, you just checked that cube of 4 is 4. So you can confidently write 4 here. What's the cube of 13? Well, we just checked that it's a 7. So again, it's the same. What's a cube of 2? It's an 8. And it's the same. Cube of 11, where we just computed is 11. Cube of 7 is 13, right? And you know, these two are equal columns, right? So this was simplified by the fact that, you know, here we happen to have that E equals D for n equals 15, but not in general. Okay, so whoever looks at this slide, I mean these notes, you know, don't think of this as a general thing, right? So this things that these two powers were the same was a coincidence because of small primes taken here. Okay, look at the textbook for more examples, wait for discussion for more examples, and of course, do one in your homework. Thank you so much. See you next time.